everyone. Thanks for coming. It looks like you guys are really into microservices. So can you get everybody hear me? Great. So this talk is about Poweramp, which is the microservice platform that we implemented at iHeartRadio. And it's going to be an overview of it and what's the architecture and some of the implementation details and also like some tools we implemented, we developed to support this microservice platform. So, so first, let's look at the. I was asked to add this to the slides. Basically, you can rate this session, so please remember to do that. But let's start the presentation with this architecture overview of the microservice platform we call Poweramp at iHeartRadio. So the core thing is the Akka Cluster. Our apps are all part of Akka Cluster. They are clustered together using Akka Cluster technology. And on the top, you see an API gateway. That's a Play app. That's where all HTTP requests coming in. And inside that's also inside Akka Cluster. All the microservices are actually implemented as Akka apps, as you can see here and here and here. They are microservices that are also deployed into the Akka cluster. So the API gateway can talk to them through Akka protocol and as well, and the microservices themselves can talk to each other through Akka protocol. So, and then they can talk to data stores, external services, or message queues, which are, where the information comes from, the data comes from. So those are outside the Akka cluster. So, we also have a command center, which you can control all the microservices, give them commands using this interface, and we also have a matrix monitor that can give you matrix monitoring for all the microservices running. So that's the basic idea. What's interesting here is that we have this so-called API gateway and Akka services distributed endpoints. What actually means is that one thing that usually is interesting is that where you define HTTP endpoints. You can define them at HTTP endpoints at the API gateway, or you can define them at each Akka service app. So each microservice define their own HTTP services, REST endpoints. That's a common practice. The other common practice is define those HTTP endpoints at the API gateway. But the downside of defining each HTTP service at each Akka services, HTTP endpoints at Akka services, is that then you have to make sure that you take care of the service registry and the service discovery, and also it encourages inter-microservice communication to happen at the HTTP level. So that's one approach. The other approach is to actually define them in HTTP gateway. And we take a different approach, which I'm going to cover in after the next slide. So first, why we choose to use Akka Cluster for clustering our microservices, because, well, it's out-of-the-box clustering infrastructure, so why not use it? And it also provides a loose coupling between microservices through a typed binary protocol. So, it's Akka messages, it's typed, and it's also binary protocol, so you don't, it's a little bit performance gain from there. And also, it provides a transparent programming model within or across the microservices. So you can write your programming in Akka actors, and either it's within a microservice or it's across the microservice. It's the same programming model. So if you want to refactor, it's a lot easier. And the last two is, you get high resiliency, performance, and scalability built in with Akka Cluster, and you also get a strong community and commercial support from the Akka community. So that's why we use Akka Cluster. So now let's talk about our approach for defining HTTP REST endpoints. So we call this distributed endpoints, meaning that you actually define your HTTP endpoints in the microservice, the Akka app itself. However, those HTTP endpoints are served by the API gateway, which is the Play app. And the way, and we developed this tool called Asobo, is open source, that allow you to remotely define HTTP endpoints in your microservice, in your Akka app, and just send that definition to the API gateway. And that API gateway, the Play app will basically create routes, HTTP routes for those endpoints. And then once they get the request for those endpoints, they get to actually forward the request to work through a so-called work pipeline to the actual Akka app. And then Akka app do all the job, do the work, the data processing, and then send them back to the API gateway. So, and then the API gateway finally serve that HTTP response back to the client. So this way, why we do this? It allows you to implement cross-cutting API logic, HTTP related, in the API gateway. For example, authentication, error handling, validation, you can all implement them in the API gateway. And that allows you to deploy a cross-cutting logic without redeploying microservices. It's one common thing, for example, I have authentication, and a lot of my microservice needs them. Now I change the logic. What does that mean? If you implement this logic through a library and through a binary dependency by those microservices, now you have to redeploy all the microservices. And this way allows you to get away from that. So you can evolve your cross-cutting logic, all those validation, error handling, and authentication separately, independent from the microservices. And this also allows, and you can remain, for the microservices themselves can remain independent, right? Meaning they don't depend at all on the API. If you have a new microservices, you simply write your own HTTP endpoints in the microservice, and you deploy it to the cluster, and this microservice will be added to the API gateway registry, and it will have all the endpoints defined by this new microservice exposed to the public API. So, and if you take this microservice off the cluster, those endpoints will be removed from the API gateway. So that way, your microservice is independently deployable and independently developed. So that's why distributed endpoints. And this is how, this is a code example of how we develop this. And if you look at this is actually the routes file that actually is at the Akka microservice side. So you write this routes file, which looks like a play routes file a lot, especially if you look at this line and this line. One is the guest, the other is the post. They actually exactly are using the same syntax as the play routes file, and they define those two endpoints. And you also write a controller in the actually Akka app. I call it controller just so that it resembles what we usually do as the play app, which is you write a controller that handles the message. But actually, what this controller does is to define the HTTP endpoint definition. They don't actually handle anything. They just create a definition of endpoints and send that over to the API gateway. So in this first example, you can see what it does is that I say handle get groups, and I'm going to process a get groups message, and I'm going to use a certain backend and expect a group's result from that backend and respond JSON. So that's the whole definition. And behind the scene, this DSL, we call it Asobu DSL, is using a shapeless cats and kittens to have this type-safe way to define where you want to get all the information come from. So let's look at the next example, which is create a test. So this service is about creating A/B test. It's about A/B test service. So you can create test. You can say, okay, giving user which A/B test groups this user is in. And for the second, for the create test endpoints, we can look at this example. So create test, it says process create test, and that is actually a case class, as you can see here. And it takes two entities. Take two fields. One is the author, the other is the A/B test. And as you can see, the DSL is going to say, for the author, I want to get it from the authenticated username. That has to be authenticated. This request has to be authenticated. And I'm going to use the authenticated username as the author of this A/B test. And the second field is the test. And this is another nested case class. so that we have another case class of A/B test that represents what to create, the data to create an A/B test. And that part of the information is from the body, is from the JSON body. So here you specify for the author field, I'm going to from authenticated username, and for the test field, I'm going to get it from the JSON body. And from that too, the system, I mean the REST endpoints is actually construct the create test message and send it to the backend. The backend here, as you can see, is just the actor ref passed in, and then the backend is going to do all the job, and going to the DSL said I'm going to expect a test created message back from the backend and simply respond JSON OK. And what it does is that it automatically use a formatter of test created and create a JSON out of that case class. So, but if it doesn't, if the backend doesn't return a test created, it will return an error message like a 500 or 404, depending on how our cross-cutting error handling message, cross-cutting error message handling mechanism defined. So that's what I'm saying. So you only write the happy pass, the bad pass, the sad pass is usually taken care of by the cross-cutting logic, the error handling, validation, and so on and so on. So that's the DSL that you can create those distributed endpoints. So the other part of the architecture is called reactive work pipelines. It's called it's powered by this open source project called Kailuo that we developed, and it's to solve an interesting problem, which is if you write your Akka app right, if you write everything right, you do everything asynchronously, which means that they don't block. So whatever requests coming in, they're just going to send that directly to the database, and without thinking twice, just wait for the database to return a result. And what that means is that if you have expected increase of incoming traffic, they're all going to hit the database, and then like a DDoS or whatever. So, and you burn down your database, that's definitely not good. So that's the main incentive of why we use this reactive work pipeline, is to make things more resilient. So we have this called smart control pressure on backend that this work pipeline provides. So the first thing it does is a little law-inspired back pressure. So it's a very primitive back pressure handling, so that if the request is not handled in time, you're going to start to reject the incoming requests. And the other part is called optimal concurrency size exploring. So what it means? So basically, what we call control pressure on the backend is that we make sure that at a certain time there's only a certain number of concurrent connection hit the database. Either it's 5 or 6 or 8, doesn't matter. But it's confined. So if you have DDoS, you won't increase that concurrency into say 1 million hitting your database. That's not going to be responsive. So, but now you have this control, you have this limit of your concurrency to hit that database, but then it becomes an arbitrary number. So this, so what number do you set? You don't know. So this optimal concurrency size exploring is basically trying to figure out what's the optimum number of concurrent connection that you can allow to hit the backend data, or either data service or external net web service. So what it does is that there are two phases. One is it explore a little bit up and down to see the neighborhood concurrency connection numbers, and then it record the performance, the matrix performance, and then that's the first part. The second stage is to optimize. So basically, it looks at neighborhood concurrency size and choose the one that has the best performance and move to there. And then to explore a little bit again, and then to optimize, which is moving to the next optimal concurrency size. So that way, it automatically explore the best or the optimum concurrent connection that you allow to hit your backend database. and it's dynamic, meaning it's keep constantly optimizing. So if a database gets more beefy or get more performance, and then it automatically increase the number of concurrent connections for that based on the performance. So we saw this in real world working for database. It stopped at a certain say number 8 or 10 concurrent connections. For some really strong web services like a Facebook web services, it go all the way to 300 concurrent connections. So that's automatically figure that out for you. A smart, what we call a smart controlled pressure on the back end. And then we also have a circuit breaker, which is pretty simple. That if you see a lot of errors from your back end, you probably want to give it a break. So, and then maybe wait a little bit and close the circuit breaker to try it again. So basically, that's the circuit breaker. And the other thing that Kailuo, which is our reactive work pipeline provides, is the matrix monitor. So that because now we know that our work is always going to come through this work pipeline, we can have better understanding of this as defined at work. So that we can see the throughput, we can see the failures, we can see inbound requests, queue lengths, expected wait time. We can also see the concurrency size, so that we know how many concurrent connections we're making to the back end, and if it's optimum, is it increasing or decreasing, what's happening. So we can see all those. These are supported by, provided also by integration to StatsD and Grafana. So the other part that we provide is actually also interesting, called distributed Swagger definition or Swagger documentation. So although your endpoints are defined at Akka app or the microservice layer, we provide the centralized Swagger documentation UI at the player at API gateway. And how is that achieved is that you write your Swagger documentation or YAML file in the routes file as comments, just like this block. And just say, summary or parameter and responses, what's the response, and so on and so on. And those are going to be submitted to the API gateway, which then generates the integrated Swagger API Swagger documentation for you, so that you have API documentation at a centralized place where your clients can, play with. You can try it with, this UI. And another thing that the Play Swagger integration does is that it gets information from not only the comments here, but also the routes definition itself, and it also look at the case class definition. So it generates a data schema for based on reflection, and look at your actual message type, and then generate the schema for that, so that it basically extract as much information as possible from your code, and to display them in the Swagger UI. I should have asked, how many of you actually used Swagger before? Cool, great. So this is also we achieved this through this open source library we call Play Swagger. We developed, and so that we can have distributed Play Swagger integration. So other things that are in our cluster are nodes monitor, which is infrastructure UI that you can see all the nodes in the cluster right now, and we adapted this from Mookie 88, but also added a bunch of functionality, like you can see the current commit, git commit shard for each service, so you know exactly what versions they are at. And also we added a thing called event monitor, which is basically a congregation of all the error and warning logs, so that you can see them in a centralized place, and you can search through them. So we didn't have to use any log congregation mechanism, just a simple web page that congregates all the logs from all the nodes in the cluster, and you can see them in a centralized place. Very useful when you do development. So the last part of the utility in Command Center is the job monitor. So we also write a lot of data processing jobs, like queue processing jobs as well, in our microservices, and you need a centralized place to start, stop them, and monitor them. And this is the tool that we created for that. So to make this all developer friendly, we also developed SBT utils, including the SBT script to bootstrap cluster, start-stop services, report services status in the cluster, and report remote cluster status. And also we do a blue-green deployment script in this SBT utils. So what allows us is to do blue-green Akka Cluster deployment, so that if you have any compatibility, incompatible services you want to bring into the new cluster, you can use blue-green deployment. So that's very handy for us, where you can just start SBT, you can say start catalog, and you will start catalog service, stop catalog, stop the catalog service. So you don't have to view each microservices with different SBT window. So then the next part is what's coming. First thing we want to think about is to improve the performance and the binary migration, compatibility migration for our messages between microservices. So we want to generate case classes from message types of either protobuf or Eon, the new thing from Amazon. But right now, we use case classes, which is not very, migration friendly. So that's the first thing we're thinking, and the second is multi-service versioning. So we're hoping to, we're planning to add this multi-service versioning capability in our cluster, so you can deploy different versions of the same microservice in the cluster. And if an interdependency between microservices, a service should be able to say, okay, I'm dependent on this version of that service, so I'm only going to talk to this version. If there's a new version of that service coming in, we're going to ignore that. And other things, including auto-scale services, instances, and continuous CD or continuous delivery. So those, we are using Docker, and we deploy it on AWS. So using ECS and other AWS-related DevOps tools. So that's our next step. So the open source projects that we developed for this project are Kailuo, Asobu, and Placeworker. I think Kailuo, just go over them again. Kailuo was the one that provided the reactive work pipeline that gave you the automatic concurrency detection. That automatic automatic concurrency size detection is also available through Akka router that is in Akka code. We contribute that code into Akka. So the others, so that's the first thing called Kailuo. Second one is called Asobu. It's the distributed DSL or distributed REST endpoints capability. That allows you to write your REST API endpoints in your microservice and then deploy it to a centralized play app called API Gateway. So that's the second thing Asobu is about. And the last thing is the Placeworker, which allows you to write Swagger definition in the routes file as comments and generates Swagger, the real Swagger spec, and be servable by the Swagger UI. So that's our three open source projects. So other than Akka and Play, we used cats, shapeless, and kittens for our project. I mean, I don't think I need to introduce them here, except kittens, which is relatively new. It is basically a library a small library right now, combining the ability to combining basically generic programming and functional programming together. So it's pretty awesome. I'm going to show an example of that. But before that, we have just want to shout out thanks to a group of people that are really helpful for our development. And this is our team, iHeartRadio Poweramp team, really awesome team. So let's look at something more geeky. It's our functional building block. So regularly, before functional programming, how we build application is basically function from A to B. For example, you have a get user, which is from ID, with user ID, to a user. So the problem with that building block is that first it's blocking, right? It's synchronous. And second, it throws exceptions. So what if the ID couldn't find? So that's the two main problem of that building block. So our building block that we start to use is basically a data structure that provided by cats and Scala Z as well, called actually two data structures. One is classly, and the other is XORT or XOR. You can think XORT as just an either, but it incorporates the future into it. So it's basically, you can think of it as a future of either. So, but why do you need either? Either is either left or right. So the right side is the successful case, is the success case. It's easy to understand. The left side is a reason why it didn't succeed. It could be exception. It could be the data is not found. It could be some validation error. But it's just a reason that we basically consolidate all our set paths into ADT of that we call reason. And so that's XORT. It's a future of either the thing failed due to some reason, or you get this thing out. And classly is basically wrapping a function from A to this XORT, a future reason of this thing. So you can think of the classly as just a function. But instead of returning A to B, you give it A, instead of returning B, it returns the XORT future reason of B, which is basically a future of either reason or B. So that's the actual type of our building block. So what does that give us? Sorry, before I go to there, just look at this get user example in our code, which is a class of XORT future reason ID from ID to user. So the first thing it gives you is function composition, right? So if you look at this code, say you have a case class user, and which has two fields, name and age, and it has the first method called validate user. You're passing account name, you're passing a password. The left side of the K is the from type, and the right side of the K, which is this part, is the ID, is the result type. So the first method or function is basically from K, from the account and password to ID. And then you got another one which is from ID to name. Then you can just compose them, validate user, and then get user name, right? It's just like composition. It's just like function composition, although your function is actually a lot more complicated. They are non-blocking, they are asynchronous, and they also don't throw exceptions. they just return either. And you can just compose like this. So the second type of composition you can do with this classly is monadic composition. So this classly is actually a monad. So you can just use this thing. You can say get user name, get user age, and you use a new user from name and age. And that gives you a class, a K of from ID to user. So because this get username takes ID and this get user age takes ID too. So when you do this monadic composition, they just like monads. So that's very convenient to use. One thing I have to point out is that to use this, you have to, there's this Scala thing called SI2712, which is a bug that prevents you to use this. But very fortunately, just a week ago, I think maybe 2 weeks ago, a guy called Miles Sabin developed a Scala compiler plugin that fixed this. So if you use that compiler plugin, you can use this way, just to point that out. So that's the caveat. So, and the last type of composition is called generic composition. That is going to use the power of kittens. So instead of a for loop, you can simply say, I want the name field to be get user name and the age field to be a get user age, and that gives me a user out. And that's very, to me, very elegant and a very new way to compose functionalities. You can write, you can have each get username and get user age is a microservice, and you can compose microservice this way. You can say, well, this fields, they are from this microservice, and for those fields are from that microservice, and then we just put them together, and we get the congregating information out, and that's very easy to read and easy to understand, and there's basically no boilerplate. So that basically concludes the presentation, which is pretty short. All right, thank you guys.